Hey guys, welcome to the CS Classroom. Today we're going to cover topic 16, which is system software. Now, topic 16 on the A-level exam consists of two parts. The first one being purposes of an operating system, and the second one being translation software. Right now, we're going to cover the first part, which talks about how an operating system functions, and it specifically focuses on how processes are managed, interrupts and handling, and virtual memory, as well as the dynamics behind virtual memory. Now, topic 16 in general consists of one 5 to 7 point question. So while it's not super important, still, if you know it, that's an extra 5 to 7 points, sometimes more. Now, in this particular topic, the first concept we're going to cover is the role of the user interface. Now, a user interface generally refers to any graphical elements on a computer screen we can use to control what's going on in the computer. So think clicking, dragging, moving things around on your computer screen. These types of graphical user interface elements are used to hide the complexities of computer hardware from the user. So for example, let's say that you want to access a file on your hard drive. You can just click a few buttons and then you can open up a file. Like if you really didn't have a user interface, then you would probably have to type in a bunch of commands, go and find the address of a particular file, use that hexadecimal address to access the file, maybe call up another program to open up that file. The point is that it would just be ridiculously complex, and most people probably would never use a computer. So there are a few ways in which the user interface can be used to hide complexities of computer hardware. The first is what we just talked about, which is the use of graphical user interfaces rather than command line interfaces. Graphical user interfaces being those things you can see on the monitor, and command line interfaces being represented by things like the terminal or the command prompt, where you're mainly just typing in lines of text to make things happen on your computer. The second way is through the use of device drivers. Now, device drivers are basically programs that allow you to really easily connect and use hardware on your computer. So basically, if you connect a mouse to your computer, then you don't really have to do anything. In like 2 seconds, you can be using it. That's the result of device drivers. If you didn't have device drivers, then you would probably have to write your own computer program and then run that program every time you want to connect a device. It would just be an absolute pain to set things up and use them. The next is tasks carried out in the background. So oftentimes in your operating system is carrying out tasks that you can't see to keep things working as you want them to be working. So for example, every time you open a program, the operating system is going to be conducting different tasks to make running that program possible. But in the user interface, you don't actually see that, right? So the user interface is only showing you what it is that you want to see and what you care about, when in reality, there's a lot of stuff that's going on in the background that it hides. Now, the final way in which the user interface can hide the complexities of computer hardware is through making data transfer and retrieval as easy as possible. Like a lot of what you're doing on the computer is reading data, editing data, or saving data in some way. And through the user interface, you have things like folders, you have save buttons, you have all kinds of really easy to use tools to make all those processes possible in a quick and easy to use way. And this is the result of the user interface. So I would say that that's one of the big pluses of having a user interface. You can interact with data storage without having to really deal with a lot of the complexity that underlies those interactions. Now, the next thing I want to talk about is processes. Now, you may not be aware of this unless you kind of dug into the workings of your computer, but a process is what underlines every program or task in your computer. Now, when you were talking about the central processing unit in a previous unit, you've probably come across processes at that point. Basically, anytime you open up a program or anytime any sort of task takes place, that is a process. That becomes a process that needs to be executed by the CPU or the central processing unit. So for example, if you click a button on an icon to open a program, there are one or more processes that are then initiated that need to be executed on your CPU in order for the program to actually open that corresponds to that icon. Now, there are a few things to know about processes. So as we just said, a process is launched when a new program is launched. Second, processes do not interfere with each other. So every time you initiate a process, that's sort of its own self-isolated set of tasks or actions that are going to be made possible, executed, and then made possible by the CPU. Next thing that's quite important is that processors have their own space in RAM. Sorry, not processors, but rather processes have their own space in RAM. So when you initiate a process, that's automatically going to allocate some space in the RAM or the primary storage, because of the fact that to really do anything on the computer, you're going to need to be moving around, editing, or saving some amount of data. So some space is necessary, and that space is going to live in the RAM. And if you remember back to learning about just the fundamentals of computers, the RAM is responsible for holding all the data in currently running programs. Now, the final use of processes is in multitasking. So multitasking basically means that you can do multiple things at the same time. And I guess maybe this isn't a usage of processes, but rather this is something that processes are heavily involved in. But multitasking is basically when multiple processes are running at the same time. So if processes interfered with each other, and they didn't have their own space in RAM, if everything was kind of a mess, I don't think multitasking would be possible. So this whole concept of processes makes doing multiple different tasks at the same time possible in a computer system, or multitasking. Now, in order to sort of deal with processes, okay, so if you look right here, for example, this is maybe it's not very clear what this is, but this is basically a list of processes. And if you're using like Mac or Linux, it's really easy to see the list of all the processes that are being run. I think in Windows as well, but I rarely use Windows, so I don't know. I'm sure there's a command for it, like psaux or something. But there's a bunch of different processes taking place at the same time. They all have their process ID, like when they started, and different information associated with them. Now, in order for a computer to function seamlessly, in order for the user to have an effective user experience, these processes all need to be managed in such a way that they're not conflicting with each other, they're all running efficiently, they're all being executed by the CPU in a timely manner, etc. Now, to allow this management of processes to be done as seamlessly as possible, we have a data structure called the process control block. Now, as we just said, there are a multitude of processes that are taking place at any given point in time in a computer. The mechanism that allows us to manage all of these processes is called the process control block. Now, the process control block is a data structure. So it's basically something you can think of as a table that exists in your computer at all times, and that is used by the operating system to manage and maintain information about processes. So for every process that's taking place, there will be a process ID, a process state, so the current status of the process, its priority, any related information for the OS, and then locations for data storage relating to the process. Now, in our previous slide, you may have seen this picture but not understood what was going on. Now, this is basically a list of all processes that are currently being executed by your computer that you could pull up on Mac or Linux, and I'm pretty sure Windows, I think there's like a psaux process. And this is just kind of a small slice of all the processes that could be taking place. But this is representative of a lot of the information that you would find in the process control block. Now, the role of the process control block, as we said, is to manage the processes. And some different things it might do is allow us to switch between processes, to run multiple processes at the same time, which is multitasking, and just generally any process-related operations, which I know is super vague, but like there's a lot of stuff that's going on that you don't necessarily need to know about for the A-level. Multitasking is one of the big ones that you should know about the process control block. Now, in our process control block, we're going to be holding something for each process called a process state. It's essentially the status of the process. And there are three possible states that you need to know. First is running, ready, or blocked. Now, we use the running status when a program, or rather a process, is currently running on the CPU. So if it's currently running, currently being executed, it's in running state. Next, the ready state represents a process that's waiting to be run. So it's ready to go, and it's waiting to be run by the CPU. I should probably change this text because it doesn't exactly say the same thing, but basically, process is ready, it's ready to go. Whenever the CPU is done with its current operation, or whenever it's done with whatever is on its queue to be executed, then it'll go ahead and execute this process. Next, we have blocked. Now, a process can become blocked when it's been executed, but in order for further execution, a certain event needs to take place somewhere else in the system. So for example, if you're running a process that requires input from the user, that process can be executed up to an extent, but it can't proceed until the user inputs some information. So if this is the case, then that process is put into a separate queue with block status. And then once that event that's stopping it takes place, the process is brought back to the CPU to be executed. So basically, when it's blocked, we can say the process is temporarily suspended. So running means a process is currently being run. Ready means a process is ready to be executed and will be as soon as the CPU is done with the current work that's allocated to it. And then blocked means that a process has been temporarily suspended until some other necessary prerequisite event can be completed. Now, this is just like a little graph or a little diagram that shows how process states work. So we're going to have a new process. It's going to go into ready state. And then when it is ready to be executed, it will go into running state. Now, if there is some sort of event that needs to take place before it can finish being executed, then it'll actually go into waiting or blocked state. And at the point at which whatever necessary event has taken place, then it'll go back to ready state and it'll go into the queue to be further executed. Now, when any process is being executed, it goes into terminated state. Now, the new and terminated state, you don't really need to know those, but I think those are kind of intuitive anyways. Mainly for the A-level exam, you need to know ready, running, and blocked, and what they do and why they're used. Now, another process that the process control block aids in is called scheduling. Now, scheduling is the process by which the operating system determines in what order processes are executed by the CPU. And this is where the whole blocked, ready, running state all comes into play, right? Because that's going to be part of determining when and how we schedule processes to be executed. Now, this accordingly involves modifying individual process data in the process control block. And scheduling also involves resolving conflicts between two processes that need to use the same resource. So maybe two processes need to access the hard drive and make some changes to the data. The scheduling can make sure that their actions don't conflict with each other. Now, generally, the order in which processes are scheduled to run is determined algorithmically, and there are 4 different algorithms that you need to know. But before we get to that, I just want to go into a bit more depth as to why scheduling is necessary. So first, scheduling is necessary to enable multitasking. If we just have a single processor or a single core processor, then we're not going to really be able to execute processes at the same time, but we might be able, while one process is blocked, we might be able to execute another process, and etc., to give the appearance of multitasking. If we do have a multi-core processor or multiple processors, then we can have true multitasking. But still, scheduling is necessary in all of those cases. Scheduling makes sure that the CPU or CPUs are busy at all times, which essentially leads to reduced waiting times for processes to be executed and more efficiency, which leads to a better user experience because as a user, you don't need to wait for stuff to get done. Scheduling also allows certain jobs to be prioritized so that the system can run more important tasks first. Now, the algorithms that make this possible are the following. The first is the round-robin algorithm. This means that every single process is given a certain amount of time to be executed, and if it's not finished, it's blocked and placed on a queue. So this means that every process, for example, a given process, opening a window, that might be given a certain amount of time to execute it. If it's not executed in that time, then it's put on the queue and the next process is executed. Eventually, we'll get back to that process that was put in the queue, and it'll continue to be executed. So just think about every process maybe has like 5 milliseconds, and it's kind of like sorry, my handwriting is absolutely terrible. And it's kind of like a rotating sort of queue where we execute this one, this one, this one. So 1, 2, 3, and then 4, 5, 6. And then we kind of just go through the cycle, giving each process the same amount of time, and then really only offloading the process when it's been completed. This meant 5 milliseconds, by the way. Again, sorry for my handwriting. Now the next algorithm is shortest job first. So this means that processes are executed in ascending order of CPU time required. So basically the shortest tasks are executed first and the longest tasks are executed later. This means that really simple tasks aren't really held up and more processes can be executed in a shorter amount of time. Basically, we get rid of all the easy stuff. We do like the easy stuff first and then we move on to the hard stuff. Now, first come, first served means that each process enters a queue and executed one by one. Think of this as like your traditional queue, like you standing in line at an office. Every person gets handled one by one. And one of the benefits is that there's no complex logic and there's no processor overhead involved with scheduling processes. Because scheduling is an algorithm, and the more complex it is, the more resources that are going to be required in order to allow that scheduling to take place. Now the final algorithm is shortest remaining time. Now this means that anytime a process is being executed, we compare the projected execution time of a potentially new process with how much time is left over for the currently running process. Now, if we find out that the new process that hasn't been executed yet will take less time than what remains for the currently running process, then we're going to do that first. So basically, we're always checking the projected execution time of a new process that hasn't been executed yet versus how much time is left for a process that's currently being executed by the CPU. And the benefit is that there's higher throughput, meaning that more processes can be executed in a given amount of time. And it kind of makes sense because the concept behind this is similar but not the same to shortest job first. Basically, if a process takes less time to execute, we're going to go ahead and prioritize that, which means that we're going to be doing the easy things first and leave the longer running processes for later. Now, all of these have benefits, which you do need to know for the A-level exam, along with a basic description of how all these algorithms work. Now, the next concept I want to talk about is interrupts and interrupt handlers. Now, an interrupt is a combination of software and hardware components that can be triggered to prioritize a process for immediate execution. So basically, if something that's super important happens that we didn't foresee happening, then we're going to use, or our computer rather, is going to use an interrupt to execute the process required to resolve that issue. Some examples of when an interrupt would be triggered would be a paper jam, when the user presses something on the keyboard, like Control-C or Control-Alt-Delta, or really anything, a software error or malfunction, or an infinite loop, which is essentially a software error or malfunction. So an interrupt gets into, so remember the process control block, we basically always have a queue of processes that are going to be executed. An interrupt gets in between that and then prioritizes a process for immediate or execution, or just increases the priority of the process. So it makes it high priority so that it gets executed as quickly as possible. Now, in order to allow interrupts to occur, we are using a combination of software and hardware components. One of those components, one of the software components, is an interrupt handler, which does interrupt handling. Now, this is basically a piece of code in the CPU that knows how to deal with interrupts. So an interrupt is triggered, interrupt handling is going to begin, allowing that process to be executed or prioritized or whatever. So basically, when we have an interrupt, the current state of the CPU is saved. Whatever process is on the CPU is put into block status and suspended. The interrupt process is executed, and then operations resume as normal, executing whatever process was currently running or whatever is on the queue, depending on the scheduling algorithm. Now, one aspect of the operating system that's super important in dealing with interrupts is the kernel. This is an OS component that's basically an intermediary between the hardware and software layers of the computer. So think about the software layers as what's in the operating system and the hardware as just the components in the computer, right? And kernels, among many other things, are responsible for managing interrupt handling. So here's how a kernel responds to interrupts. First, it detects and acknowledges the interrupts. It saves the context or current state of the currently running process in the CPU. And this includes any data and registers, program counters, etc. in the CPU. And it takes all this and it basically stores it, saves it, right? And puts the process into a block status. And then it determines the priority of interrupts. Now, there may be multiple interrupts at the same time. So the kernel is responsible for determining the priority of the interrupt as compared to other interrupts that may be taking place. Then it basically identifies and transfers control to the interrupt service routine, which is kind of our more, I guess, literal interrupt handler. And this is a block of code responsible for handling a specific type of interrupt. So there might be a variety of different interrupts, like an interrupt when the user types on the keyboard or when there's a software error. And there's going to be an interrupt service routine that corresponds to all of these. And the kernel is going to transfer control to the specific interrupt service routine that corresponds to the type of interrupt to further deal with it. Then the interrupt is executed, and the kernel restores CPU context and instructs the CPU to control normal operations. So the kernel is kind of the overall manager in dealing with interrupts and interrupt handling. So let's take a look at this diagram to further explore how kernels work. Now, let's say we've got a process that is currently executing, but then we have an interrupt that's triggered by some external event. This interrupt stops the process from executing, it results in an exception, and that process is then put into block status. The interrupt is handled by the kernel. Well, actually, the kernel also leads to the process being stopped, but the interrupt is going to go to the kernel. The kernel is going to call up the interrupt service routine. So basically, it's going to be coordinating, sort of managing the interrupt handling. And once the interrupt has been executed and dealt with, then we leave the kernel, and then we go back to the execution of the original process. So now the next concept we're going to talk about is going to be virtual memory. So basically, we use virtual memory when the RAM is overloaded. So if we are executing too many programs at the same time and too much RAM is being taken up, data is temporarily sent to secondary storage, meaning our hard drive. Now, in our hard drive, there's going to be a section of our hard drive called virtual memory. And that virtual memory is where this data that can't be stored in the RAM is going to be sent. So basically, overflow from the RAM is being sent to the virtual memory. More specifically, we can say that data that isn't currently needed, so data that's not currently related to currently running programs and is lesser used, is going to be sent to virtual memory to make space for what is immediately necessary. And when there is free space in RAM, then data from virtual memory, which is located on the hard disk, will slowly be sent back. So virtual memory is basically serving as a place to put data that we don't currently need, so that there's enough space in the RAM for currently running programs or data that will be needed in the near future. And when there is free space in the RAM, we can bring data back from the virtual memory. Now, one thing to take into consideration is that accessing data in virtual memory takes more time than accessing data in RAM. So a hard disk or secondary storage is always going to be slower than RAM. Hence, we don't want to have to use virtual memory, but if it's necessary, then we will. But programs are always going to run faster. Well, just generally, our computer is always going to run faster when it's reading off RAM. Now, when we're dealing with virtual memory, the OS is basically going to manage virtual memory by transferring pages of data from RAM to secondary storage. So pages are basically chunks of data in a fixed size that basically the RAM is organized into, and that can be transferred to virtual memory. So pages are going to serve as the unit of data that gets transferred between virtual memory and between the main memory, RAM. Virtual memory being on the hard drive, main memory being in the RAM. Moreover, when we're working with virtual memory and paging, as this process is called, of of transferring pages of data between virtual memory and RAM, we're going to have a larger virtual address space. So normally we'd have a limited physical address space for our RAM that only allows us to access addresses in our RAM. But then once we start using virtual memory, we expand the number of addresses that we're using to include that data that has been transferred to virtual memory. Basically, we're putting them all into one address space, so we have addresses for all the data, both in RAM and virtual memory. And this is something that takes place as a part of paging. But mainly what you need to know about paging is that data in RAM and in virtual memory are organized in units called pages that are of a fixed size. And data is transferred, pages of data are transferred between the two when we're making use of virtual memory. Now, to get more deep into paging, we kind of talked about what pages are. Basically, when memory is split up into blocks, also called partitions of a fixed size, these are pages. Now, these blocks can each correspond to different programs. We're not going to have a block of memory. We're not going to have a page with data from different programs, but each page will correspond to its own program. Now, to kind of get into some terminology, we're talking about physical memory. We're talking about RAM. It was also referred to as main memory. We're talking about logical memory. We're talking about our virtual memory. Now, I want to go back here. I think it was probably a bit confusing, but I just kind of referred to pages as being both in the RAM and in our virtual memory or disk storage, right? So the reality is actually that when we have data in our RAM, then it's actually referred to as a frame. So these are still fixed blocks and they'll have the same size as pages in our logical memory, but it's just that when they're in the RAM, we call them frames. So technically we have pages in both the RAM and the virtual memory, and they're being transferred within each other or between each other, but they're just called frames when they're in the RAM. Now, programs are generally allocated a number of pages, so blocks of data, that are slightly more than what is needed, and a page table is used to keep track of pages in virtual memory and recall the correct pages. So a page table kind of serves as a ledger or sort of an organizational tool for us to keep track of what pages match up to what programs, and allow us to recall the correct pages when they need to be used currently by the user. Now, one way of managing memory all over in our physical memory and our virtual memory was paging. Another method that we could use is called segmentation. Now, segmentation works similarly to paging, logistically, but the difference is that we have variable size segments. So that means that every block is not going to be the same size, but they'll all be different sizes, depending usually on what type of data is being stored in the program. And it's oftentimes less efficient, partly because segmentation requires more overhead because the correct segment size needs to be calculated and certain things need to be done in order for segmentation to take place. But if we're talking about virtual memory, basically it works the same as paging. You're transferring segments to and from your virtual memory. And I will say though, segmentation is not recommended for virtual memory. It's just another method of memory management that you need to know for the A-level exam. And one other difference between paging and segmentation is that while the OS was responsible, the operating system was responsible for paging, with segmentation, the compiler that's responsible for compiling the code that makes up a program is responsible for allocating data into segments and kind of determining what size they are. So let's say you've written a C++ program, and this is going to be compiled, right? C++ is a language whose code needs to be compiled in order to be used. So basically what's going to happen is that compiler is going to determine what parts of the program's data go into what segments, and then what the sizes of those segments are going to be. So it's going to be predetermined by the program, not by the operating system, as in paging. And that's probably one of the reasons why it's less efficient, because it's not really taking into consideration all the other programs that are functioning in the computer. Anyways, to summarize, segmentation, unlike paging, has blocks of data of different sizes, It can be used in virtual memory, but it's not because it's less efficient. And segment sizes and segments in general are allocated based on the compiler that's compiling code into a program rather than the operating system as in paging. And this table basically outlines what I just said. Faster to access pages and segments, slower to access segments than pages. Now, the last concept you need to know for this section is called disk thrashing. Kind of funny if you think about it. It's like beating a disk. But the reality of what it is actually isn't that far from the literal wording. So basically what this is, disk thrashing is a situation that occurs in computer systems when the operating system spends a significant amount of time like swapping data between physical memory and virtual memory. So if your computer is always having to move data between physical memory and virtual memory, then disk thrashing takes place. And disk thrashing basically just means heavy use of the hard disk. And because it's putting so much like load and it's using the hard disk so much, some of the effects are data loss and corruption, high disk activity, which reduces the life of the hard drive, and reduced multitasking capability because you're spending a lot of time and honestly like a lot of processing power in this swapping between physical memory and virtual memory. So your ability to multitask and just function at a high level in general is reduced. Now, some of the causes of disk thrashing are insufficient RAM, overcommitting memory to like basically allowing programs to function that use more memory than you have. Excessive multitasking, which again, running like a computer game, your browser, and I don't know, like some sort of like data science calculation at the same time. Then also poor memory management. So if you remember before, we went through like scheduling algorithms, and scheduling algorithms are really just the tip of the iceberg in terms of managing the functionality of the computer. We also have algorithms that are related to how memory is managed in the computer. And if these are inefficient or these are just not appropriate for the task, then these can lead to disk thrashing. Because basically they're reducing the efficiency of memory management. Okay, now let's take a look at part 2. I'm not going to go over the practice questions for part 1 because they're mostly theory-based, and I think it's pretty easy to look at the mark schemes to see the answers to the questions and get a feel for the exam-based questions that way. Now, in part 2, we're going to talk about interpreters and compilers, stages of compilation, so we're going to be focusing a bit more on compilers, and something called Backus-Naur Form and reverse Polish notation. Now, the first topic is going to be interpreters. So interpreters are generally used with interpreted programming languages like Python, JavaScript, PHP, etc. Now, these go through code and execute it line by line. So every time you go from one line of code to another, so for example, well, these are compilers, but every time you go down from one line of code to another, so the first line, second line, third line, fourth line, it executes this line, goes to the second line, executes this line, goes to the third line, and etc. And by execution, we mean that each line of code is converted to machine code, and then that machine code is executed by the CPU. Because if you remember, the CPU can only understand machine code. Now, if there are any errors during execution, so for example, if we have an error on line 3 of our code, then execution is going to stop right there, and we're going to see an output. So we basically stop executing and just show an error message. Now, every time we want to run a program, we're going to go through interpreting the program line by line, which is a bit different from compilation, as we'll see in our next example. Another thing to keep in mind is that when we're working with loops, so let's say, for example, we have for I in range 1 to 2 or 1 to 3. Then all of this code right here inside the loop, that code that's in a loop is not going to get interpreted once, but it's going to get interpreted for every iteration of the loop. So basically, when we go through a loop, every piece of code that's in the loop gets interpreted for every time we're running that loop. And that might not be so important. I mean, I saw it in the mark scheme, but still, I think it gives you a better vantage point from which to understand how interpreters work. We're literally going line by line and executing every line of code. So executing the previous line of code before the next line of code. And in loops, we're just interpreting whatever code is there for as many times as we're running the loop. Now, with compilers, we're taking a slightly different approach. So some examples of compiled languages are C++, Java, and Swift. But there are many compiled languages, just as there are many interpreted languages. Now, with compilers, we're first going to convert something called source code to something called object code. And this process of going from source code right here to object code right here, which is really just ones and zeros, machine code, is done by a compiler and is called compilation. So with compilers and compiled languages, we're converting from source code to object code, or machine code. Object code is going to be in binary, and then that object code can be executed by the CPU. So as we said, this is an example of object code, and this is something we can send straight to the CPU for compilation. Now, depending on how the compiler works and the language works, object code may also be an intermediate form. So object code may look different from this hello world.o, and it may need to go through another step to be converted to binary. But the point is that we're not executing every line of code line by line as we did with an interpreter. We're taking the entire code, or the entire source code, so all the code, putting it through a compiler, and then generating a file with object code. And then we're going to execute all of that object code. So there's an extra step from interpreters. Now, if we compare interpreters side by side, first by process, we can say interpreters execute code line by line, while compilers translate the entire code to machine code before execution. One of the implications is that every time we run code using an interpreter, we need to reinterpret and execute each line of code. Versus with the compiler, once we compile our code to object code, then we don't need to really go through that process of translation to machine code again. With an interpreter, we're doing that every single time we run the program. With a compiler, we just need to convert our program to machine code once, and then we can execute that machine code. Now, we can say that interpreters are generally slower because code is analyzed and executed simultaneously. So remember, we need to go through, the interpreter needs to read the code and then execute it before moving on to the next line. Versus with the compiler, we've already done all of the analysis. So we've already converted everything to machine code. And then we just need to execute it. We just need to execute the object code that is produced. So there aren't these two processes where we're converting our code to machine code and executing it happening simultaneously with compilers as they are with interpreters. Now, next, with interpreters, we're not consuming as much energy or as much memory because of the fact that we're basically loading a line of code into memory, executing it, discarding it, and then moving on. So we're not loading all the code into the memory up front. It's literally just going to be line by line, with each line being discarded after it's been executed. Versus with the compiler, we're taking our entire program and we're producing this object code. So basically, we're putting our entire program into memory at once before we execute it. So with an interpreter, we'll have individual lines of code in memory, one at a time, versus with compilers, we'll have the entire source code in memory. And this may not seem like a big deal, but because especially we're looking at it like a simple hello world program here. But imagine if you have a program with thousands of files, then it can really make a difference. Finally, we'll take a look at security. So with security, in terms of security, interpreters are generally less secure because if you want someone, for example, to run your Python code, you need to send them that code so it can then be interpreted. Versus with a compiler, if you wanted someone to execute your C++ code, you could just compile it and then send them this. You could just send them the object code, which really can't be turned back into source code and is pretty much impossible to read. I mean, it's not impossible, but it's pretty difficult to just go ahead and read binary and then turn it into source code. So it's not easily reverse engineered versus with an interpreter, you pretty much have to hand a user all of the code they need to run the program. Hence, we can say compilers, or we can say programs that are compiled using compiler-based programming languages are more secure than those that are interpreted, generally. Now, we're going to dive a bit deeper into compilation. Broadly speaking, there are four stages of compilation that you need to know for the A-level exam. This should be 3 and 4. Now the first is lexical analysis. So with lexical analysis, you're going to be converting a sequence of characters into a sequence of tokens. So let's take a closer look at lexical analysis before we move on. So what do we mean by converting a sequence of characters into a sequence of tokens? So this process of converting characters into tokens has 2 stages. First, removing all of the white space and comments. So we're just going to have text, just the text code. And then we're going to convert our source code into tokens. Now, basically, when we're converting into tokens, we're using a table called the keyword table, and we're matching up each keyword or symbol with a particular string or number that is our token. So instead of having like our normal Python code or normal C code, we're going to end up with a bunch of numbers and or strings that represent things like print or if or for. They basically represent everything about our program. And we'll just have a sequence of those. So it's not just keywords or symbols, but variables, constants, and other identifiers like function and class names. And while these might be unique to a specific program, they might not be part of the programming language. Before we turn our program into tokens, we're going to add them to this keyword table that we're using to convert all of our basically our source code into a bunch of strings and numbers. So here's an example, a really simple example right here. So if you look at this table, basically we have a bunch of different like keywords from programming language. I mean, I guess we could imagine this is like, I don't know, Python or something like that. And all of them have codes with them. Now, technically, these codes are what we could call our tokens, even though it's kind of like written the other way around. But basically, instead of having a program with if, else, while, for, etc., we would want a program that would be like 1, and then something else, 2, 3, 4, etc. Now, this isn't a complete table, but this is a good example of what a table would look like. We might have an adjacent symbol table in order to have all that stuff that's specific to our program, but you don't need to know much about that. So basically, to kind of summarize lexical analysis, we're converting all of our source code into tokens, and each part of our source code, like for example, if, print, equals, any symbols that we're using in our source code, or variable names, or class names, etc., those are all going to be put onto a keyword table, and they're all going to have a string or number assigned to them. And then based on that keyword table, we're going to go ahead and we're going to convert all of our code to a sequence of string or numbers. And so we should just end up with just like a sequence of strings or numbers that represents our source code at the end of lexical analysis. Now, with syntax analysis, this is a little bit different. With syntax analysis, we're using parsing algorithms to interpreting the meaning of our tokens. So with lexical analysis, we've basically just converted our program into a bunch of strings and numbers. With syntax analysis, we're actually taking taking the order of those strings and symbols into account, and then we're interpreting it to get to figure out what it all means, like what it all does. And we're also going to check if our code follows the rules of the programming language. So whether it follows the syntax of Python, C++, whatever programming language you're using. Lexical analysis is converting it into, so again, to go over lexical analysis is converting our program into a sequence of tokens or strings or numbers. Syntax analysis is making sense of that sequence of tokens that we now have, and also checking if it follows the rules of the programming language. Then our next step is going to be optimization. Now, optimization is simply kind of taking our code and trying to change it into a form that's more optimal, that works faster. So this is an example of optimization. Here we have a method called add10, and through optimization, we've kind of reduced all the functionality in this code to this right here. And because we have less lines of code, we're using less memory, and arguably just this code will execute faster. So we've got lexical analysis, syntax analysis, and then we've got optimization. And then our last step is going to be where we're really changing our code into machine code or binary. And that's going to be our code generation. So there are two things that can happen. We can either go straight from source code to binary, so 0, 1, 0, 0, etc. Or we could convert it to an intermediate type of code, which would then be converted eventually into binary. But the point is, the code generation, we're going from source code to machine code that can be executed by the CPU. Now that being said, let's move on to some of the weirder parts of this particular tutorial, which are Backus-Naur Form and reverse Polish notation. Okay, so Backus-Naur Form basically consists of a set of symbols and rules that are used to describe the syntax of a programming language. And as a part of Backus-Naur form problems, we're also going to be looking at syntax diagrams to describe how certain parts of code or certain pieces of text can be constructed. Now this is an example of Backus-Naur Form. So right here in a program we have digits, integers, and floating point. And this is something you would see in any program, right? Like in any program you're going to have digits, integers, and floating point. But for our programming language, this is telling us what a digit can be, what an integer could be, and what floating point could be. And that's represented by this weird symbol with the 4 dots and the equals. So this is basically telling us that a digit needs to be either between 0 and 9, an integer needs to be one of these digits, or it needs to be a combination of a digit and an integer. So basically a digit and another digit. And floating point needs to be an integer with a dot and an integer. So we're basically using Backus-Naur Form here to tell us what the rules, basically what the syntax is, or the rules of a programming language. Now let's see how this translates into an A-level problem. Okay, so in order to get a better understanding of how BNF works in the context of the A-level exam, let's go ahead and work through a practice problem. So in this practice problem right here, we've got several syntax diagrams. Then we've also got another different type of diagram. It's not exactly a syntax diagram, but we'll get into that in a second. But looking at this particular syntax diagram right here on the top, the first one. So right here, we've got basically everything that should and can be used in this particular programming language. So the syntax diagram is basically representing what can be used in the programming language. What would be correct syntax? And we basically have 4 operators we can use. The plus sign, minus sign, multiplication sign, division sign. We have 5 different symbols we can use. We have 5 letters we can use, and we have 10 digits we can use. Any characters that we use outside of this are not going to be correct because they're not in the syntax diagram. So our first sort of task is to state whether, well, actually, before we get to our first task, let's start with B right here. So it says complete the Backus-Naur form for the syntax diagrams shown. Now we saw this notation in our previous slide. So if you go back right here, we know that this is like 4 dots and equals. We're using that to basically signify what a digit is, or what an integer is, or what a floating point is. So basically to show what each type of, let's say, information, or really, I mean, to an extent, data type, consists of in this programming language. So right here, if we want to answer this question, complete the Backus-Naur form for the syntax diagrams shown. So in the first question for symbol, basically want to show everything that is a symbol. So that could be a $sign, a percentage sign, an and sign, an at symbol, or a pound sign. And actually, let's just make sure that's the syntax that's used in the A-level exam. So yeah, right here we've got these or symbols right here, right? It's the same as the slide we saw before. And now if we go back to a letter, we just want to write down everything that is a letter, right? And that's going to be everything that's right here. So we're going to have A, D, P, R, and y. And basically that answers question B, and that's how we can take a syntax diagram and actually turn it into the notation that we saw right here, the Backus-Naur form. So while this is a syntax diagram up here, this is really going to be our Backus-Naur form. Now, having done that, let's go back to the first question, which is A. State whether each of the following passwords is valid or invalid, and give a reason for your choice. So basically, in order to deal with this problem, we need to look at this diagram right here. And let's take a look at kind of an expanded version so I can more easily explain it. So basically, in this type of diagram, we were basically getting a format for how a particular string is supposed to look like in a programming language. So what this is telling us is that a password in this programming language, or in this programming context even, has to follow a certain format. It needs to have letters, digits, and symbols. But more specifically, how this works is we could input a password and then effectively check whether it follows these rules. So if we input a password, first we need to have a letter. That's our first type of thing. And this letter, digit, and symbol, these words, correspond to our syntax diagram right here. So we need to have a letter that fits into the letter, basically the letter syntax diagram, and then a digit that's one of those 10 digits, and then a symbol that's one of those 5 symbols. So we need to have so the first thing that needs to be in a password is going to be a letter, but we have this symbol right here, this sort of looping symbol, and that means that we can have as many letters as we want. But after those letters, we need to then have a digit, and we can have as many digits as we want, as denoted by this looping symbol, and then we're going to have a symbol, and we can have as many symbols as we want, similarly denoted by this looping symbol. So given that we know that, let's go ahead and let's see whether these different passwords are valid or invalid, because that's what the question's asking us. So we know that so if you look at dpad $99, we've got 4 letters, and then we have 2 digits, and then we've got a symbol. So that kind of actually follows the format of the password. And let's just make sure that dpad exists. Dpad are all valid letters. And so we have D, P, A, and D. So those are valid letters. All the digits are valid. 9 and 9 are both digits. And then a symbol, do we have a dollar symbol? Yeah, so right here we've got a dollar symbol as part of our syntax diagram. So we not only have our characters in the correct order, but they're also valid according to our syntax diagram. Now next right here, we've got 3 letters, we've got a symbol, and then we've got 2 numbers, right? And so this one was valid, but this one is going to be invalid because it breaks the order. So according to our syntax diagram, we need to have a letter and then a digit and then a symbol. This right here has letters, or not just a letter, but we need to have some letters, some digits, and some symbols. This one right here has some letters, it then has a symbol, and then it has digits. So it breaks the order. So you can just say wrong order. Symbols before numbers, right? And now let's take a look at our next diagram. So right here we've got ADY 123 question mark. So just looking at this does actually follow the order that we need for a password. However, the problem is that if we look at these letters right here, we have the letter Y. And the letter Y is actually not, no, that is in our syntax diagram. They're all in our syntax diagram. So I guess the letters aren't the problem. Okay, we've got 3 numbers, and those aren't the problem, but we have a question mark. So the question mark is the problem, because if you look at our symbols right here, the question mark is not a valid symbol. This one is invalid because we have the right order, but we're using an invalid symbol. So we can just write invalid symbol, and then we can just specify that that's the question mark right there. And that's basically how you work with a syntax diagram. So in this question, we got to take a look at our writing in Backus-Naur form and then looking at syntax diagrams. Let's go ahead and let's look at some other questions so we can further understand how this works. So right here it says, this is another question. It says an identifier begins with 1 or more letters followed by 0 digits or 1 digit or more digits. Valid letters and digits are shown in the syntax diagram on page 6. Draw a syntax diagram for an identifier. So previously we were trying to identify a password. This is going to be an identifier, which may be like a function name or some sort of variable name or anything that identifies a particular piece of data in a program. So we can have one or more letters. So I guess we'll draw something like this, identifier. For drawing a syntax, actually this is a syntax diagram. Yeah, so for drawing a syntax diagram for a particular string, we can have identifier. And we kind of want to look at our example right here, right? So identifier, and then we've got letters, digits. Okay, cool. So identifier, and then we're going to have a letter. But we can have one or more letters. So we're going to draw this right here, and we can draw our little like loop symbol. Then we can have 0 digits or 1 digit, or more digits, which is weird. So we have letter, and then we can have digit, okay? So what we can do is we can go ahead and we can draw a loop like this, okay? So this loop right here signifies 1 or more digits, okay? But then we have something else also because we want to signify that we could have 0 digits. So what we're going to do is we're going to draw an arrow from here. So before we get to the loop from here to here, and this signifies that we could bypass the digit altogether if we wanted to. So we can have one or more letters followed by 0 or 1 digit or more digits. So we have identifier, then we have letter, and we have our looping arrow to show that we could have basically as many letters as we want. And then we have digit. But in digit, we have this arrow that allows us to bypass digits altogether. And then we also have digit followed by a looping arrow to show that we could have one or more digits. And this is basically how you would depict any number of digits, including 0. And I basically did use the mark scheme in order to be able to do this, but sometimes I do that. I just wanted to make sure and still explain it, just so you guys understand why the arrows are where they are. Also, I'm like, sorry for my shitty drawing. I'm just not an artist. So that's another example of a syntax diagram. This is something new that we learned that we hadn't seen before. Also, we have an alternative way of depicting syntax diagrams. So weirdly right here, so this basically means what this is saying is the same thing, but this indicates that we need to have one letter. And once we have one letter, we could actually just bypass, using this arrow right here, we could bypass any further letters, or we could have additional letters before moving on to digits. And then the digit notation is the same, where we can bypass digits, signifying that we don't necessarily need a digit. But if we do it, we could have one or we could have more, symbolized by this. And okay, so we've got another syntax diagram right here. Let's see if there are any questions associated with this. Okay, so it says, write the Backus-Naur Form notation of the syntax diagram for character. So what characters do we have? Okay, we've got character right here. So the way we would do this is we would just have like character. We'd have our 4 dots like that. We're gonna do an equal sign. And then we need to write all the characters we have. So let's see, dollar, percentage, and. So dollar, percentage, star. I don't know how I'm gonna draw the star. Like that, I guess. That's a bit ridiculous. And then pound sign. So I don't know if I mentioned it explicitly earlier, but this like vertical slash basically means or. So it could be this or this or this or this, right? And we're separating all of those by dashes or by these vertical signs. Yeah, I just wanted to point that out. That was kind of clear to me, but I don't know if it's clear to the audience that's what that means. So let's go check the mark scheme, and yeah, we're good to go right here. You got 1 point for just this like character for this notation right here, and then another point for what the actual characters are, with this being the complete answer. And we've got yet another BNF problem, or we have another BNF A-level question. It says a password must begin with a character and be followed by one or more digits or capital letters. So this is like actually quite a different format. Must begin with a character and be followed by one or more digits or capital letters. I guess, wait, what is a character actually? Do we have any character notation? It's actually based on this question. So a character is going to be a symbol. So this is not going to be the first one. Instead, we can start with with like a dollar symbol, and then one or more cap digits or capital letters. So we'll just do that right there. Right here it says a valid password is represented by the syntax diagram. So write the BNF notation of the syntax diagram for password. Okay, so we actually need to represent this diagram in BNF notation. Okay, so how this is going to work is it's going to look a lot like this. We actually have to connect different types of, basically different types of information, or different, you could say data types even. It's not going to be as clean as this one like we saw in previous questions. So let's go ahead and take another look at the problem and see how we can solve it. Okay, so first off, we're going to have a character. So we're going to have password, and then the first thing we're going to have is a character. And then we have this whole construction of like one or more digits or capital letters. Now that's kind of complicated, so we're just going to call that code. And then we're going to define what code actually is. So character code, and then we need to define what code actually is. So basically code is going to be one or more digits or capital letters. So we need to kind of represent every possible combination. So it could be like just a digit, or it could be just a capital letter, okay? Or this is kind of recursive. It could be a code, so like some digit or capital letter, followed by a digit. Actually, it could be a code and a digit. Or it could be another code and a capital letter. So this may be kind of confusing, but it's kind of recursive in a sense. And this is how we can represent that we can not only have one digit and one capital letter, but also a digit and then a capital letter. So we could have some construction like just digit and capital letter followed by a digit, and then, or we could have a capital letter followed by another capital letter, or we could have like some complex code, something that's like a combination, and that could be followed by a digit. So this actually allows us to kind of describe this. It could be followed by one or more digits or capital letters. So it could just be a combination of digits and capital letters. It could be a digit, it could be a capital letter. And having this code, having this sort of recursive code, then digit, and then code, then capital letters, allows us to make that combination possible. So this is probably the most complex BNF problem that you would have. So yeah, this one was actually a 4-point question. And it was, I guess, so I think this is 1 point. This is another point. And then, let's see, 1 mark for each marking point. And I guess this would have been 1 point, and this would have been 1 point. So yeah, right here we have digit, capital letter, digit, code, capital letter, code. Okay, so now let's move on to a topic called reverse Polish notation, which really has very little in common with the previous topic, except for the fact that they both have notation in their name. And the reason we're covering this now is because it is part of the same topic in the A-level curriculum. Now, reverse Polish notation is basically a way for compilers to more easily evaluate arithmetic expressions. So let's say we have an arithmetic expression like this, 10 plus 5 times 3. Now for a compiler to evaluate this, it would basically need to check where the parentheses are, evaluate what's inside, then do additional arithmetic expressions. In many ways, this involves things like stacks and can involve things like recursion and gets pretty complicated. However, if it's changed to this format, where we have the arithmetic values on one side and the operators on the other side from left to right, it becomes a lot more performance and memory efficient to be able to make sense of this and basically convert it into machine code. So compilers will use reverse Polish notation when they're taking source code and converting it to machine code. Now this is also called postfix notation because we have our operators after the values that they're acting upon. Now to give you a better example of how this works, we're going to go through it and solve some problems where we're converting between regular or infix notation and reverse Polish notation and back. And then we'll talk about the more theoretical aspects of this. So right here, what we want to do is we want to convert from infix, which is a regular expression we're used to seeing in like source code, to RPN. And we're going to start by dealing with what's in parentheses. So we have AB minus for this expression. We have AC plus for this expression right here. And I'm going to go ahead and put those together. AB minus, AC plus. And then we're actually just multiplying those by each other. So there's that, and then we can just write a little multiplication sign right here. And then once we've done that, we're doing, like the next value we're going to have is going to be 7. So we've kind of dealt with everything right in here. And the next value we're going to have is 7. And we're just doing division by that. So I'm going to do 7 and then division. So it's almost like we're working from the inside out with whatever parentheses we have. And as you can see, we've got the right answer right here. Now to give more clarity, let's take a look at another question. And this one's going to be the opposite, where we're actually writing the RPN expression as an infix expression. So going from something in reverse Polish notation to something that we would write in source code. Okay, so we have AB division. So we're going to do, I guess what we're going to do is we're going to do AB, A divided by B, right there. And then the next thing we have is like 4 times the multiplication sign. So I guess what we're going to do is we're going to multiply this by 4. And then we have AB plus. So we've also got like A plus B. Then we have the multiplication sign. So I guess what we're going to do is we're going to do this multiplied by this. And that's pretty much it. So I want to go back and review what we just did there and just kind of review the process, and actually for both of them. So right here, we're starting from the left and moving to the right. So for example, when we had AB and then division sign, that means we need to stop and we need to do some math. Like that operator needs to be used, okay? So that's why we had A times B, or we had A divided by B. So we have A divided by B, and then we have 4 star AB plus minus. And we can write it like this initially just to kind of see how things work. So then we have 4, and then we have another arithmetic operator. And if we have another arithmetic operator, we need to stop and we need to do some arithmetic. So that's how we end up with A divided by B times 4. And we're just going to go ahead and write the rest in Polish notation. So we have AB plus minus. So now we've just got AB plus. So we've got A divided by B times 4 and then AB plus. And the plus comes after these two, so that means it's going to apply to just those two. So we're going to have A divided by B times 4 and then A plus B. And then we have a minus sign, and we just have a minus sign left over. But we have these operations, we have these two operations that aren't connected to each other. So we might as well, we can just go and put the minus sign in there, and it's going to connect both of those. It's going to apply to those respective expressions. Now, this isn't really actually that straightforward. So let's go ahead and let's just do more examples so you can get a better idea of how it works. Okay, so evaluate the RPN expression where A equals 17, B equals 3, C equals 48, and D equals 12. So basically this is the same as going from RPN to infix like we did in our previous problem. But once we do that, we're going to put in numbers to get an actual value. So let's start with AB plus. Okay, so we've got AB plus right here, and that means that we're stopping at the operator and we're going to do A plus B. And then we have CD division, which means, okay, so we're going to do C divided by D. And at the end, we have this division sign, and that can't really apply to anything else besides the terms A plus B and C divided by D. So we're going to do this. And now that we've done that, we can substitute some values in. We can do 17 plus 3. And then we can divide by 48 divided by 12. So basically we end up with 20 divided by 4 equals 5. And yeah, that's pretty much it. I don't actually think we had to solve it. We just had to, well, I think we should probably solve it, but whatever. This is actually what you were getting points for, this, and that was 2 points. And cool, some more examples. Like, I'm trying to do as many examples for this as possible because it's kind of difficult to explain. I figure if I do more examples, you'll understand it better. So that's why I'm doing this. Okay, so moving on. So right here, we've got a times b plus b minus d plus 15. So we're going to start out, like, to start from left to right. We've got a times b. So that means that we probably want to do ab, or a times b, or ab and then multiplication. And then, let's see, we have plus b minus d. So I'm probably going to say, okay, this one's actually a bit difficult. So we have, okay, I know we got the first part right, ab star. And now we're going to add b. So we're not going to have the operator just yet. We're just going to have b. And I think it makes sense to have plus at this point, because that means we'd have a times b plus b. And then we're going to have d, and then minus, and then 15, and then plus. Let's see if that was right. Yeah, I guess that was actually. Times b plus d. And the reason this was a little bit different is because we didn't really have any parentheses, right? So like, for example, if we had a times b, and we did that, and we had plus b minus d plus 15, then I guess we would have like ab star, we would have bd minus, we'd have plus to like deal with both of those, and then we'd have 15, and then we'd have plus. So the parentheses actually do make a difference, as weird as that is. Okay, let's move on to another question. So right here it says write the RPN expression in fixed form. So we're going from RPN to like regular form. So what we're going to do, we have AB and then operator. So we're going to have A minus B. Okay. Then we have CD and plus. So that plus is going to apply to the C and then the D. So we're going to have CD or C plus D. And then we have a multiplication sign. So that means it needs to apply to those previous terms that are acted upon. So we're going to have A minus B times C plus D. And then we have A and then the division sign. So I think that means we're just going to multiply like all of this divided by A. Because we already we have A minus B, and then we have C plus D. And we're multiplying both of those because that's the operator that comes after those terms. And then we just have A and then the division sign randomly. So let's see whether that was right. And yeah, that was actually right. Although I guess the question is, was it actually, is it A minus B times, so is it just C plus D divided by A? And then A minus B times that? Or, it's actually a good question. Let's go ahead and let's give it a try and see what we get. And then whatever we get, we get. So, although I guess it doesn't really matter because if you think about order of operations, it'd kind of be the same thing. All right, whatever. So we're going to go with this. We're going to have A minus B. So we're going to have 5 minus 10, which is times C plus D. So 5 minus 10 divided by 27, or times 27 plus 12. So negative 5 times 39 divided by 5. So we're going to end up with negative 39. And that was actually the answer. So I guess this is correct right here. So this first expression was correct. Okay, so to summarize this part of the tutorial, or rather just really reverse Polish notation, I guess the approach when converting from infix to reverse Polish notation is to start on the left side, and then for the first two operators, you're going to have those two operators, so like AB and then star. And then you need to look at the next operator and the next expression, I guess, right? Because we had AB star, and then our next operator was going to be B. So, well, okay, we have plus B, so that means that then we need to have B and then plus, because that plus is not only going to apply here, but also here as well. And then we have minus D, so we're going to have D minus, and then 15 plus. And so you're kind of just going with what terms you have. Like, again, if we had parentheses right here, like B minus D, then we probably have BD minus together. And then these would be the two terms that we're going to be adding together. And then for RPN to infix, you're basically looking at terms that are together, like A, B, C, D, and then completing expressions on those terms. And then we might have something like this, where we're going to have to put together other groups of terms that are behind it. Okay, now as promised, let's swing back to the theoretical questions. So the first theoretical questions explain why RPN is used to carry out the evaluation of expressions. Now, there are broadly three reasons. The first is that we can evaluate expressions from left to right rather than skipping around, which, as I may have said before, can lead to performance improvements, like just make it more efficient in order to evaluate expressions in large programs. We don't need to take parentheses into account. We don't need to take order of operations into account either. And collectively, this makes it a lot less ambiguous as to what arithmetic operations they're trying to accomplish, like just easier for us to accurately evaluate expressions. So if we go to the mark scheme, it says the same thing because I kind of took this from the mark scheme. The bottom line is that reverse Polish notation provides an unambiguous method of representing an expression. Now, the next question is, identify with reasons a data structure that could be used to evaluate an expression in RPN. Now, in my opinion, the answer is going to be stack. And that kind of has to do with what we saw right here. So we can add our values to the stack, 3, 10, and then 5. And then we could also add our arithmetic operators. And I mean, we could do that a couple of different ways. We could add those at the bottom of the stack or the top of the stack. But anyways, actually I guess top of the stack. But so we could have plus right here like this, and then multiplication. And then we could pop those off and then use those to deal with the further values and then push the result back on. So in my opinion, a stack is the most intuitive way to evaluate expressions using RPN. And the reason for that is just that the pushing and popping of operators and values into the stack more just closely corresponds with the process of RPN. And that's sort of the answer we have right here. The operands are popped from the stack in the reverse order to how they were pushed. And this basically mimics the order of reverse Polish notation. Now that brings us to the end of our tutorial right here. And I hope you found this useful. If you did, please remember to like and subscribe to the channel. Now, I will be putting up weekly or bi-weekly videos until I cover the entire curriculum, so please stay tuned. Also, I'm currently working on a course that is focused on teaching machine learning to high schoolers. So if you're interested in that and you want to find out more about it, or really just find out when it comes out, then go ahead and look at the link in the description to subscribe to get an update when the course is out. Anyways, have a nice day.